Very good morning to everyone. In this lecture, EC8791 Embedded and Real-Time Systems, Department of Electronics and Communication Engineering, Unit 5 Process and Real-Time Operating System. In previous session, we are going to discuss the introduction of the real-time operating system in multitask and multiple real-time operating systems. And also, we discussed how to the system can be processed in multi-rate of communication over a shared memory or inter-process communication mechanisms, and how to the schedule we are allocated through the real-time operating system, and what are the system performance. It is evaluating performance of the real-time systems. Now today we are going to discuss the power optimization strategies for process in real-time systems. It is a power is a major issue in electronics industry areas. Here the introduction, a power management policies is a strategy for determining when to perform certain power management operations. The system can be designed based on the static or dynamic power management mechanism. It is a major role. So we can how to save the power strategy. So number one, to avoiding a power shutdown mode can cost unnecessary power, and powering down too soon can cause several performance penalties, and re-entering the run mode typically costs a considerable amount of time. A straightforward method is to power up the system when a request is received. So the predictive shutdown method, it is a goal is to predict when the next response will be made and start the system just before the time, saving a requester to start up the time. It may guess about the activity of patterns based on the probabilistic models of expected behavior. This can cause two type of problems. First one is the requester may have to wait for a activity period. In the worst case, the requester may not make a deadline due to the delay occurred by the system. So we are predict the power consumption method in different categories. So we can discuss the L-shaped usage distribution method. It is a very simple technique is to use the fixed time. If the system does not receive the input during an interval of length, it is shut down. So the power shutdown wait for a period T of before the returning to the power on mode. In this distribution, the ideal period after a long active period is usually very short, and the length of the ideal period after a short active period is uniformly distributed. Because based on the distribution, the shutdown when the active period length was below a threshold, putting the system in the vertical position of the L distribution method. We can see the structure, the L-shaped distribution method, the off time and on time interval due to the time, fixed time interval. So the shutdown interval varies widely and the shutdown interval is short. So we can discuss the advanced configuration and power interfacing, that is a ACPI, advanced configuration and power interfacing. It is an open industry standard for power management system. It is designed to compatible with a wide variety of operating system and the decision modules, that is it determines the power management actions. in the hardware platform and also the application oriented devices, device drivers, and also we are using the operating system, and also we are using the configuration and power interfacing methodology. So the advanced configuration and power interface, it support the following basic global power states. So here the mechanical offset in which the system consume no power. So the soft off state which require the full operating system rebooted to restore the mechanism to the working conditions. This state has four substrate. That is a S1, S2, S4, G1, G0. So the S1 is a low wake up latency with no loss of system data, and S2 is indicated that it is substrate allocation. The S2 is a low wake up latency state which is a loss of CPU and system catch state S3. A low wake up latency state in which all the system state except for main memory is lost. The S4, the lowest power sleeping state in which all the devices are turned off. So the G1, the sleeping state in which the system appear to be off. And G0, the working state in which the system is fully usable, the legal state in which the system does not compile with the advanced configuration and power interfacing mode. So in this advanced communication or configuration and power interfacing method, it is a full of operating system to reboot the restore the mechanism to working the conditions in the different subset of rules. That's why the latency legally state in which the system does not compile or with these configurations are power interfacing modules. So in this diagram we are using the different driver, and also we are using the operating system in kernel, the advanced configuration power interfacing driver, and the interpreted and AML notations, and ACPI tables and ACPI registers and ACPI BIOS. So we are using the real operating system to manage the power consumption, and also we are applying the different set of applications modules. So this is the global power state standardization method. So the sleeping state and also the working state and also the legal state, we have to use the appeared to off condition or full unstable or usable conditions. We are not compiled with the configurations or power module states. So we have consumed the power level. So in this lecture we are discussed the power optimization strategy for real-time operating environmental in embedded system design. In upcoming session we are going to discuss the design examples of real-time operating system. Thank you for watching this video.